Hello everybody and welcome to page 143 on the workbook. And we are going to give an illustration of a big theorem that we've been leading up to kind of through this entire section 6.2. What we're going to come up with at the end of this is what's known as the orthogonal projection of a vector onto a subspace. Okay, so let's read this together. So we're starting with a vector y and v and a subspace w that we're representing as just kind of a plane so that we can picture it. And here's what we'd like to do. We'd like to find two vectors u and z. One of them is going to be in that plane w, and the other is going to be in w perp. Remember, that was the set of all vectors that were perpendicular to w. And we'd like to be able to write the y that we started with as a sum of those two vectors. Okay, well, how would that look in terms of this picture? Well, one way to get those two vectors y and z is to just think in terms of a projection. We're going to take this y and imagine projecting it straight down into the plane w. And what we wind up with is a vector here in the plane. That's the u that we were referring to the left. And then the vector z is this one. Notice that those two vectors graphically fit the description, okay, because u is sitting in the plane, so it's in w, and z is perpendicular to the plane, okay, meaning that we've got a right angle going on there. Okay, and the question is, how do we calculate those two vectors u and z? Okay, well, kind of the key is to start with an orthogonal basis for w, and luckily, we have Gram-Schmidt, so we know how to do that. And that's a problem that we can solve. Okay, so there's an orthogonal basis for this subspace W that we're talking about. And we're going to make a couple of observations that are going to lead us to a way of finding these vectors. Okay, so assuming that the z and the u exist, there are a couple of things that would have to be true. Okay, first of all, since u is in our subspace, it has to be expressible as a linear combination of our basis, okay, this set that we have here. So there have to be scalars so that u is equal to some linear combination of all of those vi's. Okay, there's one thing that has to be true. Okay, and secondly, another thing that has to be true is that the inner product of z with vj has to be 0 for every single j. Okay, do you see why that's true? Okay, because the sets in our base, or I'm sorry, the vectors in our basis up here, those are all in the set w, and so all of them have to be perpendicular to this vector z because z is perpendicular to that entire subspace. Okay, so that's where that statement comes from. Just a reminder that both of these two statements kind of came from the fact that of assuming that the u and the z in the above diagram exist. Okay, so we're going to try to put those two facts together. See if we can arrive at a way of actually calculating these vectors u and z. Okay, so we'll start with what the picture is telling us, that y is equal to u plus z. Take that equation and just solve it for z. Okay, so z is y minus u, and now we're going to go back up to the two observations that we made starting with this one, that the inner product of z with vj is 0. Okay, so if we take that, notice that z from the statement above here is y minus u, and u can be written in this way. So we can rewrite the vector z as being just y minus that entire sum. And we know that the inner product of that with vj has to be 0. Okay, so this statement that we're making really just comes from 1 and 2 above, observations 1 and 2. Okay, let's take that and just start working with it algebraically. Okay, so we can break that inner product up using just properties of the inner product. So linearity lets us sort of break that into this sort of a form. Okay, if we continue working with that, use linearity again. Okay, I'm going to do one other thing too, and just take this whole inner product term and move it over to the right-hand side. So if we add that to the other side and use the linearity again to take that summation out, here's what we end up with. AI times the inner product of VI with VJ. And we've danced this dance a couple of times already. You might remember being at this step in a proof a couple of times. This inner product is going to be 0 whenever I is not equal to j, because we started out with an orthogonal set. Okay, so that underlined part is 0 unless I equals j. So that whole sum that we're looking at there collapses down into just one term, and here's what we would wind up with. Okay, the inner product of y with vj is just the one term in this sum where I is equal to j. That's going to look like aj times the inner product of vj with itself, which we can write as the length of vj squared. Okay, take that equation and solve it for aj, and we come up with a formula that looks kind of familiar. We've seen it a couple of times before. Okay, there's our formula for the coefficient. Okay, that tells us what we would need to do to build the vector u. Okay, this projection of the vector y. Okay, if we look back at our picture up here, the projection of this vector y down into the plane w. Okay, so if we summarize all of this, we get Theorem 6.6. Okay, and this is describing the same situation that we started with at the top of the page. We start with a finite dimensional subspace of an inner product space and some vector that's in our vector space. Okay, we can project it down onto the subspace W and get these unique vectors u and z in W and W perp whose sum is equal to y. Okay, and if we have an orthogonal basis for W, we get this formula for u. It looks like the sum from 1 to k, inner product of y with vi times vi. Okay, but wait a minute. I thought that this coefficient that we had here was supposed to be this formula that we derived above. Okay, well here it really is that formula, but notice we added a hypothesis here. This basis is orthonormal, which means that the length that you see down here is actually 1. So the formula that we derived above just collapses down to this simpler form that we have here. Okay, and just a couple of notes on this. This vector u is very special, and so we give it a name. It's called the orthogonal projection of y onto w. Okay, and then we'll make the comment that if beta is an orthogonal basis, maybe it's not orthonormal. Okay, so we're kind of throwing away the hypothesis that we have unit vectors, then we can still do this. Okay, but the formula for u is going to be a little bit more complicated. Okay, this time we're going to get the inner product of y with VA over the length of VI squared times VI. You might notice that agrees exactly, okay, with the formula for AJ that we derived up there. Okay, and then finally, one comment just that might help you understand what the significance of this orthogonal projection is that we've calculated. You can think of it as the unique vector in W that's closest to y. It's the best approximation of the vector y that lives in the subspace W. Okay, in other words, if you measured the distance between y and u, you would find that that's the smallest distance of any other separation that you could get between y and other vectors in W. That's the significance. Okay, and so we will do an example of this together and then put it to work for us in the next section to come up with the least squares approximation.